Hello students, welcome to EPG Pathshala. I am Professor P03 from Jammu. Today we are going to discuss about a module entitled Electron and Neutron Diffraction under paper Crystallography and Crystal Growth. So students, let us see what we are going to learn on this module. We will be learning electron and neutron diffraction, Davison and Germer experiment, Thomson's experiments, neutron diffraction techniques, and structural studies of magnetic crystals. Electron diffraction. In 1924, the French physicist Louis de Broglie suggested that some matter might exhibit wave-like properties under some suitable conditions. It means that matter, like radiation, has a dual nature. According to him, a moving particle of matter has always got a wave associated with it. The wavelength of the associated wave is given by an equation popularly known as de Broglie equation. Thus lambda is equal to h upon mass into velocity, which is equal to h upon p, where p stands for the momentum. This is an expression for the de Broglie wavelength, which translated in physical language means that a material particle of mass m moving with a velocity v has a wave associated with it. The associated wavelength is given by the ratio of Planck's constant h to the momentum mass to the velocity equal to p, that's the momentum of the particle. According to relativity principle, the momentum p of a photon of energy h nu is given by h nu upon c, where nu stands for frequency and c for the velocity of light. So p is equal to h nu upon c, which will be equal to h upon lambda, or lambda is equal to h by p. We know that kinetic energy of the particle E is equal to 1/2 mv square, or lambda is equal to h upon mass into the velocity equal to h upon under root of twice me. For particle s moving with very high velocity, approaching the velocity of light c, we have to apply relativistic correction to the above equation. According to Einstein's equation, E is equal to mc square minus mo c square, and so m is equal to m0 upon under root of 1 minus v square by c square, where m is the actual mass and m0 is the rest mass. Hence the relativistic equation for the wavelength becomes lambda equal to h upon under root of twice m0 e into 1 plus e upon twice m0 c square. The factor within brackets 1 plus e upon twice m0 c square raised to minus 1 by 2 of this equation forms the relativistic correction factor. The wavelengths associated with different material particles such as electrons, protons, atoms, molecules, etc. can be found out on application of the relation lambda is equal to h upon mass into velocity. Considering electrons of the cathode rays, one has to use the relation 1/2 mv square equal to E capital V upon 300, where m is the mass of the electron, v its velocity, assumed to be far below that of light, and as such in the range of non-relativistic speed. Small e, the charge on the electron in ESU, and capital V, the potential difference between the electrodes of the discharge tube expressed in volts. M square V square is equal to 2me capital V upon 300, or m into small v is equal to under root of m e capital V upon 150. So lambda is equal to h upon mv. Therefore, it is equal to h into under root of 150 upon mev. Now, since h is equal to 6.55 into 10 raised to the power minus 27, m is equal to 9 into 10 raised to the power minus 28 g, and E is equal to 4.77 into 10 raised to the power minus 10 ESU. Therefore, lambda will come out to be equal to under root of 150 by V into 10 raised to the power minus 8 centimeters. When the potential difference is maintained at 150 volts, the wavelength associated with the electron is equal to 1 angstrom. For potential difference, capital V, equal to 15,000 volts, the wavelength associated with the electron turns out to be 0.1 angstrom. These values fall within the range of wavelengths of X-rays. Davison and Germer experiment. De Broglie had predicted electron waves, in general particle waves, as has already been described in the equation. Two American physicists, Davison and Germer, experimentally confirmed the same in 1927 by measuring the de Broglie wavelengths for slow electrons using diffraction methods. The experimental setup is shown schematically in figure 11.1. Capital E is an electron gun which produces beam of electrons. The filament, capital T, is made of tungsten, which is heated so as to emit electrons as a result of thermionic emission. S1, S2, and S3 are the slits to collimate the electron beam into a fine parallel pencil. A suitable electric field of predetermined potential difference is applied by a battery V so that the electrons emitted by the heated tungsten filament get sufficiently accelerated. The final pencil of electrons is then allowed to fall on a target symbolized by capital N, which is a single large crystal of nickel. There is an arrangement for rotating target N about an axis parallel to the axis of the incident beam of electrons. Capital F is a Faraday cylinder called as collector, which is connected to a very sensitive galvanometer, capital G. The collector is movable along a graduated scale, CC, which is circular so as to be able to receive the electrons which get reflected after hitting the target, that is nickel crystal, at angles ranged between 20 and 90 degrees. The collector, represented by capital F, is double-walled, each of which is insulated from the other. On striking the target, two types of electrons are to be taken care of. One type include those which are fast, having almost the incident velocity, and second type are those which are slow. The latter type are those which are secondary electrons produced as a result of collision with atoms. Since it is only the fastest electrons which are of interest. The second type of electrons being secondary and slow or stopped from entering the collector. The stoppage of the latter type of electrons in making entry into the collector is done by applying a retarding potential between the inner wall and the outer wall, because of which only the fastest electrons, that is, of the first type, are able to enter the collector and get detected by the sensitive galvanometer. The accelerating potential used in the experiment ranged somewhere between 30 to 600 volts, and the retarding potential was only 9/10 of the accelerating voltage. The whole setup was completely enclosed in a highly evacuated and degassed vessel. The target used was nickel crystal, which has face-centered cubic structure. It was cut parallel to the lattice plane 111, which is at right angles to one of the diagonals of the cube. The crystal was rotated about the axis as described earlier, so as to present the crystal plane to the incident beam and the beam entering the collector as may be required by the experiment. The experiment can be conducted in two different ways. A. The beam of electrons may be maintained at normal incidence on the surface of the crystal. In this arrangement, the diffraction effect from the surface layer acting as a plane grating is produced. For each azimuth of the crystal, a beam of electrons is made to fall normally on the surface of a crystal. The collector is moved to different positions and the galvanometer current noted. The galvanometer current is a measure of the intensity of the diffracted beam of electrons. Dependence of intensity of diffracted beam of electrons on the angle between the incident beam and the beam entering the collector, also known as co-latitude, is plotted for different voltage electrons. The curves recorded for different voltage electrons appear to be of the form as shown in figure 11.2 A to F. Figure 11.2 A to F shows curves showing dependence of the intensity of diffracted beam of electrons on angle between the incident beam and the beam entering the collector for different voltage electrons for 40 volts, 44 volts, 48 volts, 54 volts, 60 volts, and 68 volts. The bump starts appearing in the curve for 44 volt electrons. The maximum development in curve is observed for 54 volts at co-latitude of 50 degrees. For voltage greater than 54 volts, the bump gradually reduces, and at 68 volts it disappears and is not seen. The bump in these curves provides evidence for the electron waves and experimental confirmation of de Broglie concept of matter waves. The wavelength associated with 54 volt electron can be calculated using the expression lambda equal to under root of 150 by 54 angstroms, which equals 1.66 angstroms. Let us consider the diffracted beam at co-latitude of 50 degree and assume the value of interplanar spacing small d to be 2.15 angstroms in the equation for a plane reflection grating n lambda equal to d sine theta, where n is equal to 1, that is the first order. Lambda comes out to be equal to 2.15 sine 50 degrees, which equals 1.65 angstroms. B. The beam of electrons is allowed to strike obliquely on the target. In this particular arrangement, one is able to achieve diffraction effect from a space lattice. It is a situation analogous to Bragg's X-ray diffraction, and n lambda equal to 2d sine theta is appropriately applicable to this case. If the glancing angles of incidence and reflection are maintained constant, and the intensity of diffracted electrons, as measured by galvanometer current, is recorded for each electron velocity or accelerating voltage, curve with several sharp maxima are obtained as shown schematically in figure 11.3. The different maxima correspond to different orders. One can apply de Broglie's expression to calculate lambda. Lambda can also be determined using glancing angle theta and the grating spacing d by using Bragg's expression. The values of lambda given by these two different ways are found to be in agreement. Figure 11.3 shows intensity of diffracted electrons against accelerating voltage of electrons. Thomson's experiments. Professor G.P. Thomson of Scotland performed experiments on electron diffraction in 1928 using high-speed electrons in the range of 10,000 to 50,000 volts. The experimental setup used by him is shown in figure 11.4. Capital D T is a discharge tube to generate cathode rays by using induction coil. The rays are allowed to pass through a diaphragm tube so as to obtain a narrow fine pencil of electrons. These electrons, on striking a thin metallic film, capital G, of gold, aluminium, or any other, get diffracted. There is a provision for a photographic plate, capital P, to slide down and receive the electrons as they come out of the thin metallic film. Capital F is a fluorescent screen which may be used for visual examination in place of photographic plate if one so desires. The space Fg is evacuated to a high vacuum. The high-speed electrons, on passing through the thin film at capital G, get diffracted like X-rays, and the effect is seen on the photographic plate in the form of symmetrical pattern of concentric rings about a central spot, demonstrating that the diffraction pattern is because of electrons behaving as waves as shown in figure 11.5. Figure 11.5 shows concentric rings about a central spot as a result of diffraction of electrons. Following Thomson's experiment, several other scientists performed experiments on diffraction of electrons. For example, Kikuchi of Japan in 1928 obtained electron diffraction pattern of mica using 45,000 volt electrons. J.V. Hughes in 1934 used electrons of speed comparable with the speed of light and proved validity of de Broglie's law. The above said experiments and several others which followed them established vast scope of electron diffraction in the analysis of crystal structures. Now we shall talk about neutron diffraction. Diffraction of X-rays is primarily by extra nuclear electrons, and as a consequence of which it gives a diffraction that increases with atomic number. Neutron diffraction is an important probe of investigation on internal structure of crystals and has the potential of providing information which is not possible for X-rays or electrons. It is therefore important to know about the differences in X-ray and neutron diffraction processes. X-rays are scattered from the electrons associated with the atoms. The scattering of neutrons is mostly because of two factors: the nuclei in the crystal, and second, the magnetic interaction between the atoms or ions in the crystal and the neutrons, that is, between the neutrons and impaired electrons in a magnetic crystal. Only in those cases where atoms have magnetic moments are the neutrons scattered from the electrons. For example, the transition metal atoms have magnetic moments on account of impaired electrons because of interaction between magnetic moment associated with the spin of the neutron and the magnetic moment of the atoms. Magnetic scattering takes place. Since neutron scattering takes place from nuclei of atoms and not from the electrons, it becomes an effective tool to determine the position of very light atoms in the crystal. For example, hydrogen atoms in a crystal cannot be detected by X-ray diffraction technique on account of the fact that X-ray scattering produced by the electrons, one for each hydrogen atom, is too weak. The situation is different when neutrons are used as probing particles. On exposure to neutrons, light atoms like hydrogen scatters relatively strongly, because of which the position of hydrogen atoms get precisely located by using neutron diffraction. On account of their magnetic moment, neutrons interact with the magnetic field of electrons of solids. Neutron diffraction techniques are extremely valuable in structural studies of magnetic crystals. Taking the example of a non-magnetic structure of figure 11.6a and the magnetic structure of figure 11.6b, one can notice the difference between an X-ray diffraction pattern or a neutron diffraction pattern produced by the non-magnetic structure shown in figure 11.6a and the neutron diffraction pattern due to structure of figure 11.6b, which is shown in figure 11.7ab, which shows a plot of the intensity of the diffracted X-rays or neutrons I theta against theta. Figure 11.6a is for non-magnetic structure and figure 11.6b is for antiferromagnetic structure. The structure shown in figure 11.6b is an example of an antiferromagnetic crystal. In this crystal, the magnetic moments of all the atoms or ions are lined up either parallel or antiparallel to some fixed direction and arranged in such a way that neighboring atoms or ions are antiparallel and the crystal as a whole does not possess a net magnetic moment. Figure 11.7a, B shows neutron diffraction intensity against theta in A in case of non-magnetic structure of figure 11.6a and B antiferromagnetic structure in case of 11.6b. MnF2 is one example of such substances which are antiferromagnetic. Neutron diffraction experiments, though a very valuable tool, are much more complicated technically than are X-rays or electron diffraction experiments. Neutrons are available from reactors as fission byproducts and so involves a huge infrastructure. In neutron diffraction work, every requirement is much bigger than in X-ray diffraction, as for example the sample, the source, the counter and the cost. On the other hand, the X-ray source is just an X-ray tube which is portable. The source of neutrons is a nuclear reactor which is much larger, expensive and is not portable. As such, the requirements of neutron diffraction experiments are much more larger than the X-ray diffraction setup. So students, let us now summarize what we have learned in this module. We have learned diffraction of electrons by crystals, the experimental arrangement of Davison and Germer, supporting the wave-like behavior of electrons, dependence of the intensity of diffracted electrons on accelerating voltage, experimental set of Thomson's experiments on electron diffraction has been discussed. Neutron diffraction as an important probe of investigation on internal structure of crystals is explained. Thank you.